Oh, this is 3.3, concavity and the second derivative test. So you'll remember diagrams like this, where we had, for instance, the displacement graph and then the velocity function and then the acceleration function, which were derivatives of each other. And basically the derivative of a function indicates where there is a change of direction in the original function. So the zeros of the derivative indicate a change of direction, a minimum or a maximum in the original function. And we could do that for another derivative function. We could take the derivative of the derivative, and it would indicate where there is a change of direction in the derivative function. The second derivative would do that for the first derivative. Now, what we're going to talk about today is called points of inflection. And we're talking about concave up and concave down. So we want to know where the original function is concave up or concave down. And we'll talk about that further. But we also want to be able to indicate points of inflection. So what's interesting about these graphs is we can actually relate the second derivative directly up to the first derivative by just extending these dotted lines. And the point that you end up hitting is called the point of inflection. So those 2 points on the original, if I could just, right. These are points of inflection. This is where the graph changes from being concave up to being concave down. How do we find them? Well, they correspond to the zeros of the second derivative. And you can see that from where we traced up our lines from the zeros of the second derivative straight up, boom, to our points of inflection. Okay? They also end up being the max and min of the derivative function. Okay, so we used a couple words here, concave up and concave down. So let's talk about those. Concave up. This happens in intervals, and the interval can be a is less than x and x is, and x is less than b. So this just means anywhere along this x-axis, we're going to take some numbers and talk about different intervals. And it's concave up in an interval if, or we could say, because I'm writing it differently, where every tangent is below the curve. What does that mean? I'm going to actually give the definition for concave down first, just because of the way my notes are lining up. Concave down. A graph is concave down over intervals from A to B, where every tangent is above the curve. So I'll draw that out. Let's say we have a curve. And I'll give myself a bit more space. Okay, there's our curve. And if I were to draw a whole bunch of tangents along this curve, maybe a tangent here, tangent here, tangent there, and then maybe a tangent here, and tangent here. Okay, good enough. Tangent point, tangent point, tangent point, tangent point, tangent point. You can see on this part of the curve, all of the tangents are above the curve. They never come down here below the curve. So this part of my red function, my original function, is concave down. Over here, the tangent lines are below the curve. So this is concave up. Well, we can obviously see that it's concave up and concave down, but if we didn't have a graph of the function, we could still identify the intervals that are concave down and concave up based on the slope of the tangents. Where does it change from being concave down to concave up? Changes right here. Okay? What is that point called? That's the point of inflection. Point of inflection. This is concave down, and this part is concave up. Yes? So we're going to use our second derivative function to determine where these points of inflection are. And then to the left and to the right, we're going to test which intervals are concave down and which intervals are concave up. So when we do that, we're going to use what's called the second derivative test. The second derivative test. There are three options, so we have a little chart here. First one says if f prime of a, so if the value of the function, of the derivative function at a equals 0, and f double prime of a, so the value of the function, the second derivative function at a is greater than 0, then we have concave, I should say then concave up. Local, if it's concave up, that would look like this, which means there's a local min at a f of a. And again, the tangents are below the curve. Another option, if f prime of a equals 0, by the way, f prime of a equals 0, what does that mean with regard to the original curve?
Maximum or minimum?
It's a maximum or a minimum because the slope is 0. So it's a change of direction of the original curve because the slope at that point is 0. Good. If the second derivative at that point is less than 0, then concave up, and we have a local max. Sorry, concave down. Typo. Concave down, and we have a local max. And you can see that the tangent is above the curve. Last option, if, but f double prime of x. So the derivative of the original function is 0. Second derivative of the original function is 0. And f double prime of x changes its sign at A, then there's a point of inflection. At a f of A. And here I should also have the local max as A f of A. Point of inflection. Or the tangent right there. Okay, so we'll find out what we're looking for. These ones are pretty easy to understand. This one, we're going to have to see in an example in order to explain it a little bit better. Example 1. Example 1, intervals of concavity. We are given a function, f of x equals x to the power of 4 minus 6x squared minus 5. We're going to find the points of inflection, which is going to give us the intervals of concavity. So we need the first derivative, which is 4x cubed minus 12x. And we need the second derivative, which is 12x minus 12. Now in order to determine the zeros of this, that's going to give us our intervals. So we're going to determine the zeros of f double prime of x. How do we do that? We set this thing equal to 0, and we factor. Of that, we got to set that equal to 0. We factor out the 12 here. Factor the side. We get 12, and in brackets, x squared minus 1. And then, to solve for this, we're looking for values that cause x squared minus 1 to equal 0. I guess I could have done it the other way. So x squared equals 1, which means x equals positive 1, or x equals negative 1. So now these values divide the domain into 3 sections. To the left of negative 1, in between negative 1 and 1, and to the right of positive 1. So in order to do that, we're going to set up a test value chart again. Set up value slash sign chart. It's going to look like this. We have to the left of negative 1, we have what is happening at 1, we have what's happening in between, negative 1, in between negative 1 and positive 1, we have what is happening to the right of positive 1. Choosing a test value from each. Here we're going to use the test value x equals negative 2, x equals negative 1, x equals 0, x equals 2. Oh, and I'm missing a column, in case you noticed. I'm missing x equals 1. Okay, we're going to sub that into the second derivative function in order to determine the sign. So f double prime of -2 equals, if I sub -2 in here, I get -2 squared. I guess I come all the way up here. -2 squared is 4 times 12 is 48 minus 12 is 36. That is positive, which means we can do our last row at the same time. If the second derivative is positive, then that means we are concave up. And there's a minimum at x equals -2. Where x equals -1, the second derivative, that was one of our zeros, so we know it's going to be 0, which tells us that is a point of inflection. Point of inflection where x equals -1. So in order to find out what that point actually is, we just sub -1 into the original f of x, which is here. -1 to the power of 4 is +1. -1 squared is 1, so that's 1 minus 6, which is -5. Minus 5 is -10. So that is a point of inflection on the original curve. For our interval from -1 to 1, we chose test value 0, so we sub in to f double prime of 0, and when we do that, we get -12, which is negative, which means we are concave down. And we have a maximum. X value of 1, we know that's a 0, which means we have a point of inflection. And it's at 1, and just sub 1 in here, so I get 1. Same situation, it's at 1, -10. And to our interval to the right of +1, our test value is x equals 2. Sub that into the second derivative function. We end up with a value of 36, which is positive, which tells us that we are concave up. So points of inflection is where concavity changes. So you can see at -1, we go from being concave up to concave down, and then at +1 back to concave up, which would give us a good idea of drawing the graph, which we're going to do. Find the points. In example 2, we're taking a look at different critical points and basically identifying what they do there. Are they a max or a min, or are they a point of inflection? So for each function, identify the critical points. Example 2, a f of x equals x cubed minus 3x squared plus 2.
I believe this is the same one as last time. Or the same double prime elements.
Step 1, oh nice, determine critical values. We determine critical values by taking f prime, by taking the first derivative, which is 3x squared minus 6x, and go to 0, and solve. Factor out 3x, leaves us with x minus 2, which tells us that x equals 0 or x equals +2. So those are our critical numbers, critical values. In order to find our critical points, we sub into f of x to find critical points. So f of 0 is 0 cubed minus 3 times 0 squared plus 2. That's just 2. So our critical point there is 0, 2. If we sub in 2, we get 2 cubed minus 3 times 2 squared plus 2. That's 8. Minus 12 plus 2. That's going to be negative 2. So that critical point is 2, negative 2. Okay, from here, now that we have our critical points, we're going to use the second derivative to determine whether each critical point is a max or a min. Use the second derivative to determine whether each critical point is a max or a min. So here's my first derivative. F prime of x is 3x squared minus 6x. So my second derivative is 6x minus 6. And then I'm just going to sub in our x values to see if we have a negative, which would be concave down, or a positive, which would be concave up. So for f double prime of 0, we end up with negative 6. Therefore, concave down. If it's concave down, then it is a max, a local max. And we sub in 2 to our second derivative function, which would give us 6 times 2 minus 6, which would give us positive 6. Therefore, concave up, and a minimum occurs at 2, negative 2. Okay, wrapping this up, we're going to use that information to sketch the graph, and we can do a pretty accurate graph. We know a lot about it. We know its zeros, or we could at least figure out its zeros. We also know its max and its min points, and we know its y-intercept as well. It actually has a max at its y-intercept because its y-intercept right here is positive 2, and we have a maximum at positive 2. So here we go. 1, 2. There's a maximum point, critical point, at 0, 2. And then we have another one at 2, negative 2. And that is a minimum. So using that information, we can sketch our curve. Came out as a cubic, that's good. And that is the graph of f of x equals x cubed minus 3x plus 2. So it seems like a lot of work, especially since you can probably pretty much draw that without doing this. You could draw it by finding the zeros, by factoring it. But this is just another way to do it, and eventually we're going to learn some of its applications. In example 2b, again, we're going to classify the critical points. We're given the original function f of x equals x to the power of 4. We're going to follow the same steps. but we're going to find out something a little bit different along the way. So the first step is to determine the critical numbers by taking the first derivative. So first derivative is 4x to the power of 3. When we sub 0 into that, or when we solve that, we end up with the only solution is x equals 0. Now if we find the second derivative, which is 12x, and we sub our critical point, our critical value into that, f double prime of 0, we just get 0 again. So it looks like this should be, because the value of the second derivative function at our critical point is 0, it looks like this should be a point of inflection. But because our second derivative, which I did wrong, you guys got to start catching my mistakes. 12x squared. Because our second derivative function will always be positive, there will not be a change of direction. There is no sign change, which means there is no concavity at this point. So this function is always concave up. There's no change in concavity because it's always positive. This thing is always going to be concave up because f double prime of x is always greater than or equal to 0. I'm going to write some of that down. Maybe right here. Since f double prime of 0 equals 0, it looks like it should, it looks like a point of inflection. But since f double prime of x equals 12x squared is always positive, there is no change in concavity. Whatever you put in to the second derivative function for x will give you 0 or a positive number. So this thing is always concave up. Therefore, always concave up. And if we sketch the graph, you'll see that pretty easily, because the function f of x equals x to the power of 4 is basically a parabola with a flat, wide bottom. With this critical point at 0, 0. So the first derivative, we found some critical points. It was 0 at x equals 0, but x equals 0 ended up not being a point of inflection because the second derivative was also 0. It wasn't greater than or less than 0. It's only ever greater than 0 or 0, so it's no change. In example 3, we interpret derivatives and sketch. So they give us just some conditions. The second derivative of x is -2 for all x. So it's a constant. The second derivative is constant, which tells us that it is a quadratic. The original will be a quadratic because the first derivative will be linear. It'll have a variable, and the original then will be a quadratic because the degree drops by 1 each time. What else does it tell us? It tells us that f prime of -3 equals 0, and f prime of -3 equals 9. So it gives us a point on the derivative function, and it gives us a point on the original function, and we need to interpret what those things mean. Okay, here's a bunch of things that we know then. If f double prime of x is negative, what does that tell us? If the second derivative at a point is negative, then this function is always going to be concave down. What else do we know? We know that the first derivative at x equals -3 is 0. So if there is a 0 and you find the 0 of the first derivative function, that gives us one of our critical values, which means there's a max or a min there. Since it's always concave down, we know that this is where the local max is. So we have a local max at x equals -3. Then it tells us that on the original function, which is what we're trying to sketch, the value of the function at x equals -3 is 9. What does that tell us? Well, that tells us that the local max is at -3, 9. And since we already determined it was a quadratic, the information that it gives us, it's always concave down. This is essentially the vertex at -3, 9. So all we need to do is sketch a graph of this thing. And basically put a point, call that -3, 9. And sketch a graph. If we wanted to think about this, kind of thinking backwards, if you have -2 here, then your first derivative could have been something like, if this is the second derivative and we're working backwards, then the first derivative would have been -2x. And your original function then, working backwards again, would have been -x squared. That's at least the shape. This one would have had a constant, which then would have had another term and another term. But the shape of it, you can see how that originates if you're thinking backwards. If you took the derivative of this, you'd get that. If you took the derivative of this, you'd get that. So that's called integration when you work back to the original. Okay, second one. We are told f double prime of x is less than 0, so it's negative, when x is less than -1. It is positive, it's greater than 0, when x is greater than -1. Then we're told that f prime of -3 is equal to 0, so we have a critical point. We're also told f prime of 1 is equal to 0. All right, what do these things all tell us? If the second derivative is negative, then we have concave down over this interval. So concave down to the left of -1. In the next interval, the second derivative is positive, so we have concave up. Then we are told that at -3, the first derivative is equal to 0. So that's a critical point, which means it's either a max or a min. And if we look at this, if we're saying that to the left of -1 we're concave down, then that makes this a local max. And to the right of -1 we are concave up, which makes any critical value to the right of -1 a local min. And we could say this is at x equals -3, and this one is at x equals 1. And then we could sketch it. Okay, we have a local max at -3. 1, 2, 3. And we have a local min at x equals 1. So somewhere down here. Now, again, just like we learned before, this is one possible function for f of x. In the first one, we knew exactly where one of the key points was, and we knew the shape of it was going to be x squared, reflected in the x-axis. So this is actually an exact, if we had graph paper, this would be an exact drawing of the original function. In this one, we don't have any specific points that it goes through. Like we had here, we were told a point that it specifically went through. We don't have any of those here for the original function. So this is just one of the possible graphs that satisfy this equation. But really it could move up or down or have a different stretch compression. But here we go, we have a max here. It's concave down, concave up, and there we go. That's it. Second derivative, positive or negative, tells us if it's concave up or concave down over certain intervals. If the second derivative is equal to 0, then there's a point of inflection. So for instance, if you had the second derivative of the x value right there, you'd get 0. Second derivative would be 0 there, because it's a point of inflection. Practice problems that you should be able to do come from page 173. Numbers 1 through 13.